So my video was interrupted because I was looking at, I was trying to actually display one of those binary files, and for some reason my video recording software stopped working. So I have to sort of create another video to talk about the rest of the velocity model check, right? Um, so I stopped at showing you the uh, all those Z files, right? I was saying that they are actually binary files, right? But the reason that I need those files is because later on when I actually do the inversion, I need to actually multiply the kernel with the volume of each of the different cell, right? So uh, the volume of the cell has to be computed by using uh, those files, right? The horizontal grid spacing can be easily obtained because it's like a uniform, right? The lateral grid spacing is uniform, but in the curvilinear grid, the vertical grid spacing is not uniform, right? So for different latitude and longitude, for different lateral locations, the 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 vertical grid spacing varies. So in order to actually compute the volume for each of the cell or grid cell, I need those files, at least for the curvilinear grid, right? And these two sets of files, those .info files and those Z files, were created uh, for the first number set to 0, right? And then if I change the first number to 1, and then it's going to try to actually create those model files. Those model files actually store the material models, the 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 lambda, the Lamé parameters, lambda and mu, and also density at every grid point, at every spatial grid point. Not exactly every, but at those spatial grid points, recording spatial grid points, basically, right? Um, and then those recording spatial grids are actually controlled by these lines here, right? These lines here. So uh, so 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 um, so if I actually have like two different grids, right? So if I have like two different grids, then I'm supposed to have like two rows here, right? If I have like 3 or 4 different grids, then I'm supposed to have like the number of rows here is supposed to be identical to the number of rows to the number of grids. And then the three numbers are actually the decimation rate along x, y, and z directions. So here the temporal decimation rate is 5, but here the spatial decimation rate is 1, right? 5 means I'm storing every fifth temporal step. Here 1 means I'm storing every spatial grid point, right? So there's no spatial decimation at all for this particular input, right? Um, and this line is for this is actually a string for storing the directory where I want to sort of store those kind of files, those kind of grid information files, Z files, and then those model files. And then this is the directory for storing the wave fields, basically the strain fields as kind of a 4-dimensional volume, right? Um, and this directory is supposed to be simulation specific. So for different source and uh, receivers, this directory is supposed to be different. But this directory is supposed to be identical because those files, those mesh and model files do not depend upon source or receiver. They are just like all I have to do is to run those run uh, to obtain those files once per iteration, right? Um, and then for the next iteration, if I'm not changing the grid, then all I have to do is to replace those model files, those files. Those model files are needed in order to actually compute the kernels. So um, all I have to do is to update those files, right? Um, and then if I increase this number to above 1, so say 2, then SW4 is going to do simulations, do wave propagation simulations. Um, it's not gonna it's gonna skip creating those mesh files and model files. It's just gonna do straightforward wave propagation simulation to create those strain fields as 4-dimensional volumes and store those strain fields into this particular directory. Right. And then another thing that I want to sort of before I actually change this number to 1 and then run SW4 to create those model files, I need those grid recording grid files called GRD-REC recording grid. Those files are also process specific. Right, so I've got like, if I have, I'm running it on like 8 processes, so I've got like 8 files, and they are numbered according to the process ID. And those recording grid files were actually created using a Python script called skg.py. This skg.py has to be run in the same directory as inv.in, because the default behavior is that it's going to try to actually find and read this particular file in the current working directory. So in order to run this particular file, I have to do brick and then what? And then skg.py, right? It doesn't actually require any command line arguments, so all I have to do is to actually run this particular code, and then that's it. It's going to try to create those particular files, right? It's gonna read this inv.in file to actually find out the spatial decimation rate. That's something that's needed in order by this particular Python script in order to actually create those recording grids, right? So if I look at those file, those are actually text files. So these are actually ASCII files. So SW4 test. So suppose I want to look at the head of this particular file, and then the tail of this particular file. It's a kind of long, but it has a particular pattern. So the first 2 numbers are the total number of grid points in each of the subgrid, right? So I've got like 2 subgrids, right? Grid 0 has this many recording grid points in total. And then grid 1, the curvilinear grid, actually has this many grid points, recording grid points in total, right? So if I have more subgrids, then it's gonna have more rows, have more lines. That's gonna record the total number of recording grid points in each of the subgrid. And then it's gonna list the grid coordinates. It's gonna list the grid coordinates in like 3 columns, and then for the rest of the file, right? And then the way that those grid points are listed are actually different from the coordinates of SW4. So SW4 has x coordinates that's kind of a pointing. So suppose I actually closed the figure files because I didn't actually know I have to redo the entire thing. So let me try to just quickly run through this kind of create one file. So you can sort of see here that the z coordinate actually decreases, right? So it starts with 61 and ends with 1, right? So it actually goes the ordering of those recording grid points actually goes from bottom to top, right? It's not from top to bottom, right? So SW4 actually has a z coordinate that goes from top to bottom, but the ordering of those recording grid points actually goes from bottom to top, right? So z goes from 61 to 1. So right, so it's going to list the bottommost grid first. The bottommost grid, the 0th grid, has a z coordinate z grid coordinate goes from 1 to 61, right? So it's going to go from 61 to 1, and then it's going to go from 35 to 1, right? Not exactly 35. It's actually going to go from 34 to 1, actually, right? Because one of those coordinates are actually duplicating. One of those z coordinates is actually, so the topmost z coordinate for grid 0 is actually identical to the bottommost grid of grid 1, to the bottommost z coordinate of grid 1, right? So I have to actually skip 1. skip one z coordinate at the interface, right? So if we look at this particular figure, that's the interface, right? Curvilinear grid is this grid, that's grid 1, and then the Cartesian coordinate, the Cartesian grid is uniform mesh is like a grid 0, right? So at this particular interface, the z coordinates are actually identical. So when I actually inside of the skg.py, the Python script, it's gonna try to actually remove this duplicate z coordinate, right? So if we add these two numbers together, that's like 96, right? But when I actually make the model, when I actually plot the model, the global z coordinate number, z grid number is actually 95. So it's 96 subtracted 1 because we have one duplicate z coordinate, right? So skg.py, when it actually runs, it's going to try to actually remove that duplicate, right? And that duplicate is actually removed at let me just do a Emacs nw skg.py. So this line, this iz0, it's gonna record the starting z coordinate for each subgrid, right? So for the bottommost grid, that's grid 0, it's gonna start at 0 at 1. Z coordinate is gonna start at 1. But for the second subgrid, it's not gonna start with 1. It's gonna start with 2, right? And then if there's more than 1, then it's gonna try to remove all those duplicate interfaces, right? But this line of code will need to be checked for more than 2 subgrids, right? For more than 2 subgrids, I need to actually validate this line of code, but it's not too difficult to validate, right? And then the z coordinate, the z direction is like the slowest direction, right? And then the y direction, the SW4 y direction is like the fastest direction, and then the SW4 x direction is like the slowest direction. But the thing is that what I'm trying to do here is actually try to actually create those recording ordering. What I'm trying to do is to order those recording grid points in a way that's kind of consistent with the kernel code that I wrote for SWP. The SWP actually uses a different coordinate system, right? Because the SWP actually uses a coordinate system that actually goes from bottom to top, right? And then the x and y direction are kind of the opposite of the SW4, right? So for SW4, x direction is like this, y direction is like this, and then z goes down, right? But for AWP, x direction is like that. So that's the x-axis, and then y-axis is like that, and then z actually points up towards the surface, right? So for the recording grid points, z is still the slowest direction, but x and y has to be switched, right? So the y direction is very the SW4 y direction is the sort of fastest direction, right? And then if you that's sort of equivalent to SW to AWP x direction, right? That's going to be the fastest direction, right? So when I actually store the kernels on this kind of recording grid points, I have to remember that the x direction of the AWP x direction is actually the fastest direction, and then the AWP z direction is actually the slowest direction, and then it goes from bottom to top, right? So once I have created those recording grid files using skg.py, I can run SW4 with the first input, the first line of inv.in set to 1. And then SW4 is going to create those files, those model files, and then stop. Right? It's not going to do wave propagation simulation. It's going to stop. Right? If I want SW4 to actually do wave propagation simulation, I have to increase this number to 2. Right? And all those capabilities were added by myself. those are files that's kind of needed in order to compute the kernels and do the inversion later on, right? So those codes were added by myself by modifying those SWP source codes, right? And those model files are also process specific, right? So I have like 8 different model files, and those model files actually store the model parameters at every recording grid points. That's kind of inside of these recording grid description files, right? And then I have a MATLAB script for reading those MDL files. It's called read underscore MDL.m. Um, so the number of model properties or number of material properties on each grid points actually depends upon whether the simulation is going to be elastic or viscoelastic. If it's just elastic, then it's going to store lambda mu, the 2 lambda parameters, and density. That's 3 parameters per grid point, per recording grid point. But if it's viscoelastic, then it's the 2 lambda parameters, lambda and mu, density, and then QP and QS. So it's 5 parameters per grid point, right? And then the code just loops through each of the different model file, loops through the X and Y uh, process numbers, and then it's going to try to read all the different files, the model files. Right? So it's going to need the recording grid description, and then it's going to read the overall grid description for each of the process. And then it's going to read the model file, and depending upon the number of model parameters, it's going to try to extract lambda, mu, and density, and then convert them into like a matrix, and then convert them into VP and VS. Right? Because I'm looking at the shear velocity, so I'm assembling this VS for each of the different process into like a one global VS model. That's called VS underscore all. Right? So this line of code is just placing or embedding the VS model for each of the process into the correct position of the global VS array. And then this part of the code is just making the plot. Right? It's going to try to load the latitude and longitude grid, and then the topography data, and then make a plot. So that's pretty much how I actually created this particular. Let me run it again. Let me just run it again. This code is not too slow. It's quite fast, so I should be able to actually create the figure quickly. Right. Right. So that's making a map view plot, right? So you can sort of see the velocity model that's actually used in the simulation is slightly smaller than the velocity model that I actually wrote into the R file. The reason is because the simulation actually has the simulation grid is actually slightly smaller than the region that's covered by R file. So I actually shifted the origin of the simulation grid to this particular location that's slightly inside of this the entire region that's covered by the R file, right? So that's the simulation X, that's the simulation Y coordinate, right? So it's slightly shorter than the region that's spanned by the R file, and then slightly shorter in the Y direction also, right? Um, and then that's for making those map view plots. And then I also wrote a MATLAB script for plotting the cross sections. So this is for y equals to 1001 kilometer, right? So that's like a cross section that's like very, very close to the origin. That's like a cross section in this particular direction, right? And then if I run this particular script, it's gonna try to it's gonna create this kind of image, right? Again, the color scale isn't actually adjusted to the optimal color scale, but you can sort of see the velocity actually increases with depth, and then the oceanic plate actually has a higher velocity on average, right? Than the continental side. Um, so that's making just for plotting the cross sections. Um, for this particular cross section, you don't see much of a variation in topography, right? So it's pretty flat, pretty flat. But if it's a cross section that actually goes through Sierra Nevada, for example, then you're gonna see higher mountains, and variation in topography will be slightly bigger, right? Maybe I picked a wrong. I didn't actually pick a very good cross section. I probably should have picked y equals like 1,000 kilometer or something. Um, so that's for checking if I got the velocity model correct. Uh, if SW4 actually is reading the correct velocity model, that kind of information, right?